Bismillahirrahmanirrahim. This is an example of a sanitary sewer system design using SWMM. This example is taken from Water Resources Engineering by Chin, example 3.32, where a sewer network is shown with contour lines and the basic information is given. So this is just a part of the network, just as an example, so that you can understand what are the steps in the design process. Now, first of all, the information that is given in the example is like average per person sanitary load is given per day. So this is an 800 liters per day per person, which can be converted to liters per second per person. Just we can see the formula. Just we have to convert the days into seconds, and liters are there, so we can convert it into liters per second, because these are the units that we are going to use in SWMM. Similarly, in infiltration and inflow value is given, that is 70 cubic meter per day per kilometer, so we can just convert it to liters per second per meter length of the conduit. And that is again by converting the days into seconds and cubic meters into liters by multiplying it with 1000, and also kilometers to meters. Inflow at manhole number 5 is given, that is coming from the upstream, and that is 0.37 cubic meter per second, so which can be converted in liters per second again. Population density, that is 130 persons per hectare, is given, and then diameter of the pipe which is coming to join manhole number 5 is 1065 millimeters. In this case, just the first part of the whole network is written here, is shown here, and where the line number 1 to 5 are shown, and that is actually street A only, and also the link from manhole 5 to the next street along the main street, so that pipe is there. So just to look at the basic things, all these things which are displayed in white color are the given values. Here also the inward elevation for the upstream pipe which is joining in manhole number 5, the inward elevation is given. All these values which are given as in shaded as yellow, they are the first assumption in the design. So as we can see, the first assumption of the diameter is 150 millimeters of each pipe. This one 1065 is for the diameter, because the upstream diameter which is coming to join manhole 5 is 1065 millimeters. So the next pipe which is going from manhole number 5 to 12 also is assumed in the beginning to be 1065 millimeters diameter. Now cover can be calculated. Of course, the cover, as we can see, is the ground elevation which is given minus the inward elevation minus the diameter, so that gives us the cover. And as required by the problem, that minimum cover should be 2 meters, so in the beginning we just assume that 2 meters cover is there. So for all these new pipes which are joining to manhole number 5, say from 1 to 2, 2 to 3, and 3 to 5, and then from other side from 4 to 5, all these pipes they will be having a cover of 2 meters. For the cover of the pipe end which is joining manhole number 12, that has to be estimated based on the slope. Now the slope of this pipe which is from manhole number 5 to 12 is assumed to be just little bit more than the minimum slope. Minimum slope that is given here is 0.08%. That means 0.0008 is the slope, minimum slope. So the slope that is kept here is approximately 0.0009. So that's how the first assumption has been made for all these pipes, and the calculations have been done like this. So ground elevations were given, lengths were given, areas were given. So based on the areas we have calculated the values of II, and of course II can be just calculated by considering the value of liters per second per meter length. So just multiply with the length of the pipe, and length of the pipe, as we can see here, is in this column. We can find out the value of II for every pipe. Similarly, the Q average that can be found from the area. Now of course we have the area, so it has to be multiplied with the population density and per person sanitary load, and per person sanitary load is here, and of course we have to multiply it with the population density, which is again provided here as 130 persons per hectare. So we just multiply it with the area, and we are going to get the value of the Q average. Q average that will enter into manhole number 1. Similarly, for the all these Q average values are calculated, so in the same manner. And of course we have already talked about the cover, because that some of the values were given there. So that is how it is, all these values are provided. Now we come to entering the data into SWMM. When we open SWMM, so this area is the drawing area or the study area map is like that, blank. We have to set some of the things in the beginning, and the first thing that probably we have to set is the project defaults. So we go to project, go to defaults, and then here we can set the labels. For example, in my case I prefer to have the prefixes for all the components of the network. Now here we are not using rainfall or subcatchment, so we are not going to worry too much about these subscripts, but we have to give the subscripts for the junctions, outfalls and conduits. These are the most important ones. Pumps we are not using here because we are trying to do the design of a gravity based system, so that all these subscripts we can choose them. For example, here since we are talking about the manholes, so I would probably prefer the prefix as M, so just to show that it is a manhole. So if you want to save all these for your future projects as well while using SWMM, so I will just save it as my defaults for all new projects, and then I can change it later if I like. Another thing that I have to change here is the map display options, which is coming from tools and then map display options. And here of course I can see how everything will be shown there. I will just try to increase it a little bit, the symbol sizes, links also maybe I will just increase a little bit, labels and notation. This is the most important thing that we have to see here. So by default most of the time it will be unchecked, but we want to see the IDs. So we want to see in this case, as I said, in sanitary sewer system we are not talking about the rain gauge and sub catch basins, but of course we are talking about the nodes, that is the manholes, and the links. So all these IDs should be shown. Actually, values, of course, I'm not that much interested in. Similarly, the flow arrows, by default it is none, so I want to show the flow arrows based on the direction of flow, and I will say OK. So this basic setup of the software is there now. Now I have to draw my network, and a very easy way to draw the network is to bring in a background map. So we can just go to view and we bring a backdrop, and backdrop that we can load. I will just try to find it out, and I already have that backdrop map saved as a JPEG file, because these are the file types that SWMM accepts. So I will just open it and I will just put it there. Now this is the backdrop map is there. It doesn't need to be according to the scale, because I am going to input all the pipe lengths manually by myself in each pipe. So even if it is not according to scale, it will help me in drawing the network actually. Now this backdrop map is there. If this backdrop map is too much clear, then of course you can make it a little bit with a lighter color. So for example, for this backdrop map, if I say that it is going to be a watermark, so in the background I can see it, but it will not affect my drawing of the layout of the network. And as we know from the tutorial for SWMM, we have already seen probably that the first thing that we have to draw are the junctions. So we just draw the junctions. So I will just follow the same numbering so that I have almost the same arrangement of all my junctions and pipes. So my junction number 1 or manhole number 1 is here, manhole number 2, manhole number 3, number 4, number 5. And then of course I need to have an outfall. Of course I'm not, as I said, I'm just going to talk about this first part, so I have to put an outfall somewhere. But if you are doing the whole system, then of course your outfall will be probably here or here. If you are designing only A, B and C, then probably you can put your outfall here. But in my case here in this example, I'm just talking about up to this area, that is the street A only. So I will just put my outfall. I will select outfall from here and I will put it here. So this is my outfall. I need to now draw the pipes. One more thing which probably I should change before I move ahead is the map display options. I think I need to in fact increase the font size of my labels, because it is rather small. Okay, so now I think it is little bit better. And now I will draw the pipes, and again I will try to follow the same numbering as in the example, so that I can directly put in the data. So from manhole number 1 to manhole number 2 is pipe number 1, then from here to here is pipe number 2, then from here to manhole number 5, and then from manhole number 4 to manhole number 5, and then the last one is from manhole number 5 to my in my case the outfall. So these are, and as we can see, as we have drawn them in the same direction, the flow arrows are already being displayed. Let me just make the size of these arrows also a little bit bigger so that I can see them clearly. So the arrows are shown there, and all these arrows are representing what I actually wanted, the direction of flow in each pipe, because I wanted the flow should come to manhole number 5 from all the way from manhole number 1, and then from manhole number 4 also to come there, and from manhole 5 to the outfall. This was my intended direction of the sewage. So it's already there. Now I just need to enter the data. So I click here, and then I just have to enter every for the manholes I have to enter the elevations, and of course the depth of the manhole, and for every conduit or the pipe, of course I have to enter the diameter, the length. Also at the manholes I have to enter the value of the flow rate, the inflow that has to go there. And of course when the inflow is there, then I have to enter the pattern as well. Now the pattern that we shall see from that is given at another place, so I will bring it, and then I will show you how to enter the pattern as well. So here first of all we are going to enter the values of the input parameters at manhole number 1. So I will just double click, and here for the inflows I will say that now first of all there is a direct inflow which is coming from the upstream, that is only at manhole number 5. So for direct flow I will not enter anything except the value of the II flow. So II flow I will assume that it is going to be entering at manhole number 1, although we can consider that because the inflow will be entering all over the length of the pipe because of the infiltration, but inflow is also included. So we are going to consider that at manhole number 1 instead of manhole number 2 for this length of the pipe. So the first value for II that I have, as we saw in our Excel sheet before, so that was 0.0429, and there is no pattern for that because it is just a constant value, it will stay there forever. For the dry weather flow, of course I'm going to enter an average value, that is the Q average, and that is 0.5657 as we calculated from our Excel sheet. Now here I have to enter the pattern. So the pattern of course will be based on what we have from the which is given, right? So that is the given value. So based on that we are going to enter the pattern there. Now for example, if we are using the design the same pattern as given in the design project, so that can be entered there. So let's see if we can just enter the pattern here. So here for the time being the pattern is, for example, given because this all the values are we are giving by the way the hourly pattern, not the daily pattern. We can just name it pattern 1 for example, and I'm just going to put just random values here, just because I want to just let you do the rest of the stuff yourself. So for example here from 12 a.m. to say 5 a.m. I will just put sorry, I had to go there. 0.5 for example, and I think that I'm just assuming, like by this pattern, if it is not given, I'm saying that during the night the sanitary load will be like 50% of the average, so 0.5 will be multiplied. So here as well 0.5, and then after that there will be a demand which will be kind of more than the average demand in the morning. So say for example it is 2 times the average demand, again it is 2 times the average demand, and then maybe in the evening again, for example here will be more than the average demand. So just we have to be, when we are setting up our own system of the demand or of the sanitary load pattern, then we have to think about that the average of this 24 hours duration must be equal to 1, because in 24 hours the average flow is being supplied, but during 24 hours sometimes it is more and then sometimes it is less. So the sanitary load or sewage which is coming out of the houses is sometimes it is higher, sometimes it is lower, but the average over 24 hours should be 1. That means the factor. Yeah, so that's how we are going to use it. Now pattern 1 we have selected, so for manhole number 1 we have just entered this pattern, and that's all for the input values for the flow. So flow values are entered. We are not doing any treatment. Invert elevation again we have already calculated for manhole number 1, and that is the upper elevation, for upper invert elevation, the upper edge of the pipe. So that is manhole number 1. So 62.85 we calculated. Maximum depth, of course the maximum depth should be equal to the, which is going all the way up to the ground. So here in our case we have to calculate the maximum depth, which is based on the difference of the elevation from the top, from the invert to the top. So from the invert to the top, how much is the value? That is of course 2 meters is the cover and 0.15 is the diameter of the pipe in meters. So in our case at this location it is 2.15 meters. Initial depth is the initial depth of the sewage in the pipe. We are not worried about it. So 2.15, I had to enter it. Yeah, you have to enter once you enter the value there, and all the other areas we are not concerned with because they are not related to some of them are not related to actually the sanitary sewer. So this value is entered. Same thing for manhole number 2. Now manhole number 2, again the direct flow is only the II value, and that is 0.0737, and there is no baseline pattern here. Now for the dry weather, average flow is 0.6019, and the pattern, I just need to type the name that I gave, and that is already coming up, and we say OK. so that is entered. Now we have to give the invert elevation, and the invert elevation is 61.65, and the maximum depth here again is 2.15. and manhole number 3, so again for the direct flow there is II value 0.081 and dry weather average value 0.5296, and the pattern again I need the same pattern, and that's it. And invert elevation of manhole number 3 is 60.25, and maximum depth again 2.15. and manhole number 4, so we have inflows again based on the II value 0.0721 and dry weather 1.0833, and again the pattern is same. And here also the invert elevation for manhole number 4 is 59.73, and maximum depth again 2.15, and that's it. Manhole number 5. Now for manhole number 5 we have inflow which is coming from upstream. It doesn't have a pattern, so we just need to enter it here. So from upstream we have 370 liters per second, so 370 liters per second, and II value also is there, so we shall just add it. So this is 370 point II value is also there, so that II value is 0.0559. It doesn't have a pattern. For the dry weather we have for this pipe or for this manhole 0.2046, and the pattern again is the same. Now for the invert elevation. So we know that the invert elevation for the upstream pipe which is joining in here is given, so we are just going to give the same invert elevation which is 55.35, and of course the maximum depth has to be calculated as such. So maximum depth, when we shall calculate it, so it should be like invert elevation plus the diameter, and then basically it should be subtracted from the ground elevation, so that would give us the maximum depth. So maximum depth, see, that's actually basically the difference between the invert elevation and the ground elevation. So that is approximately, if I say, is, say cover is 3.65, so 3.65 plus 1.065, so that has to be entered. So 3.65 plus 1.065, so it will become 4.69, so 4.69 will be the maximum depth of at this manhole. So that's included. Now for the pipes. For the pipes, as we said, so shape is circular. Maximum depth in case of pipes is the diameter basically. So the diameter, of course, for all these pipes we have already chosen as in meters. So in meters the diameter is 0.15. Similarly the length, so length also should be in meters. So length is given for pipe number 1, 53 meters. Now roughness, of course, will be chosen based on the material that we are using. Yeah, so I will just leave it like this based on the defaults. But in our case, when you are using a certain material, you have to find out the value of Manning's roughness coefficient, and then you put it there. So that has to be entered. So far we are not talking about the offset. So this offset is not needed here for the time being, but we shall later talk about it. So this was the data for pipe number 1. So for pipe number 2, maximum depth again 0.15 and the length is 91 meters. Roughness, I will leave it like this. Similarly for pipe number 3, 0.15 and the length is 100, and that's it. Similarly pipe number 4, 0.15 and the length is 89 meters, and that's it. And pipe number 5, the diameter now is, as we have assumed, equal to the upstream diameter, which was 1065 millimeters, which means 1.065. So 1.065 meters, and the length is 69 meters, and that's it. Now the data that we had to put there, so just for the outfall we have to give the invert elevation. So I will just give the invert elevation as the invert elevation given or we have chosen based on the slope of this pipe. So invert elevation that we have chosen based on the slope, minimum slope, is 55.29, and that's it. Nothing else is needed for the invert elevation here. So all the data that we wanted to enter is there now. We just need to if we want to see the results, we just need to run the program and see if it is okay or not. But before that I would like to save it. So let's save it as, say, tutorial P2B, for example, because I already have it there. So we save this file. Once we save it, then we run it, and we can see that the run was successful, and we can see all the results here. So the first of all I would like to see some of the results for the profiles, because that would be the most important part. In order to see the variation of the profile over time, I will just click map here, and I will plot a profile starting from manhole number 1 to the outfall, find path. Okay, so that's the profile that I see. If I run it with time, now of course I had to select the time first. I haven't done it in fact, but let us see how long this calculation has been done. So then accordingly we can change the time after going to the project options. So this computation was set like the default was for 6 hours only. So let me just change the default for the so that was in the project. So in the project for defaults I had these values should go to the program preferences. So here we have already done it. So the last thing that I wanted to see is the time series. Now for the time series I have already done it, and pattern I have already done it. So from the project options I should choose the value of, first of all, the dates. Just double click dates and you will find here, now it's today's date, so not a problem. So start analysis on at 12 o'clock, start reporting at 12 o'clock, end analysis on, so in 6 hours. So I don't want to do that. I would make it to be 24, and here I will make it to be 12 o'clock. So that means from 12 o'clock 23rd to 12 o'clock 24th. So the computation will be done for 1 day. Time steps are, I think, fine. Reporting step is 15 minutes, and all the other things are there. Runoff step, dry weather, runoff step, wet weather. Yeah, if you want to decrease it also you can decrease it. Say for example we say that it is again 15 minutes, so that is also possible. Or you want to make it more precise by putting smaller steps. This is fine, I think. So we just say OK, and then let me just save it before running it. And once it is saved, then we can run the program. So we run it and we can see that it is successfully run. We go to the map here and we just run it now. So now we can see that it started and it is going to run for 24 hours, for one whole day. And as we can see in all the pipes except the larger one, the values of the flow is very small. So the flow is actually but of course we cannot use a pipe diameter smaller than 150 millimeters because of the specifications given in the question. So we have to use the minimum pipe diameter which we have chosen, and based on that we can see that in the cross section we don't see much changes there. So let's look at the other results now. For example, based on the variable, so we just select, for example, for the, let's see first of all for the links, that means the pipes, we are going to check the velocities, that how the velocities are behaving. So the velocities for all the pipes will be shown. So we can see, oh sorry, we have to select. So we have to select the pipes C2, C3, C4, sorry, I think this one was selected twice again. So C3 and C4 and C5. So all the pipes are selected and we can see the velocities. So the velocities with time are shown here, so we can check if the velocities are less or more than say the range. We know according to the specifications that minimum velocity should be 0.6 meter per second and maximum should be of the order of 3 or 3.5 meter per second. And we can see that in all these pipes. For pipe number 1, the velocity is less than 0.6 for some time, but during 24 hours, as we can see, the velocity goes beyond 0.6 as well, which means like it is not going to be a problem. So all the velocities, as we can see here, they are within the range. Similarly, we can check the results for all the nodes as well. We want to see the nodes. So for the nodes, we can see how much is the depth of water there or the head there. So we can, let's see the depth. So for node number 1, 2, 3, 4 and 5. So we can see that. So the depth is also shown here in all the manholes. So we can see that the depth of flow is within the range of the diameter of the pipe. So similarly for the pipes also we can check it. Say for the pipes, if we want to check the depth, we can check the depth as well. So pipe number 1, 2, 3, 4 and 5. So when we check it, so we can see that the depth is actually not very large, as we said in the beginning that the depth is within the range. Even the largest diameter pipe, it is less than 50%, although it can be up to 0.75 of the pipe diameter, but it is less than 50%. So all this at all the times the flow is much small as compared to the diameter, like the depth is much smaller. So that's how we are going to run the program. And of course you can plot the graphs, for example. So the graphs can also be plotted, and a lot of other things can be done by using this program. So that's all.